So in this lesson, we are going to look at the factors that affect the rate of a chemical reaction. So the learning outcome, students should be able to investigate the effects of a number of variables on the rate of a chemical reaction, including the production of common gases and biochemical reactions. Okay, so what is the rate of a reaction? So the rate that something happens is relating to time. But when we talk about a chemical reaction, what do we mean by the rate of a reaction? So the rate of a chemical reaction tells us how quickly a chemical reaction happens. One of the slowest rates of reactions is the rusting of iron, and a really fast rate of reaction is an explosion, which is all over in a fraction of a second. So you can think about a chemical reaction, it's basically like change. Okay, so change is occurring over time. So some reactions happen really, really slow, like the rusting of iron, and other reactions happen extremely fast in seconds, like an explosion. So the rate of reaction is how quickly or how slowly a chemical reaction happens. So if we have a look at these two, so here we have two different types of reactions. So the first reaction here is we are taking H2. So what we have here, so we have two hydrogen atoms. Okay, so we have two of these, two hydrogen molecules, plus one oxygen molecule, so O2. Okay, and this reacts to give you, so you get a chemical reaction of H2O, so two H2O or water molecules, and it releases a huge amount of energy. So we have on the left hand side here, we have what's called the reactants, and over on the right hand side you have what's called the products. And this is a very quick chemical reaction. Okay, so it's actually used to propel rockets off the planet. So basically what's happening here is you have these molecules here. These molecules are coming in contact with the water, and what happens is the bonds that hold these atoms in these molecules together are broken. Okay, and then what happens is new bonds are formed. So two of these hydrogens will attach onto an oxygen, two of these hydrogens will attach onto an oxygen, and then you get a huge amount of energy being released as well. So this is a chemical reaction, and this happens very, very quickly. It's explosive. It happens rapidly. But this here is a way for chemists to represent a chemical reaction. So on the left hand side you have the reactants, and then on the right hand side you have the products. So this is a very fast reaction. And then on the other hand, you have this reaction here, which is the rusting of nails. Okay, so nails are made of iron. Okay, so when iron comes into contact with oxygen in the presence of water, what you get is you get this hydrated iron oxide, or you get this like rust that forms on it. So this rust that happens, and this takes a long time to happen. It happens over a long period of time, but nonetheless, you have the same kind of mechanism or same thing happening. You physically have, for example, so the reactants have to physically come into contact with each other, and when they come into contact with each other, then depending on if the conditions are right, there will be a reaction, so there will be a change. So another way of thinking about a chemical reaction is it's a rearrangement of, so this is the way it was starting off, and then over time, this is the way it was finishing up. Okay, so it's like a change that happens, or a reassembly of the atoms that make up the products. So in industry, it's very important to know how long it will take for a reaction to occur. So reactions can take varying amounts of time from start to finish. So chemists measure how many reactants are used up and how many products are formed over a certain period of time. So this is a way that we measure reactants. Okay, so we can set a timer. So we can set some kind of a timer, and then what happens is we can monitor, for example, how quickly either the reactants are decreasing, or we can monitor, for example, how quickly the products are forming. Okay, so we can use this as a way to measure the rate of reaction. So the rate at which the reactants are used up or the product is formed. So this is a way to kind of think about it. So reactants are getting used up and products are getting formed. So we can measure either the reduction of the reactants or the increase of the products being formed. And a useful way to think about this is this idea of what's called particle theory. So during a chemical reaction, the particles in the reactants are moving all the time. The rate of a reaction simply depends on how often and how hard the reactant particles collide with each other. So for the particles to react, they must collide with enough energy to break the bonds in the molecules. Once the bonds are broken, the atoms can rearrange to make the new products. And increasing the rate of a reaction involves increasing the number of successful collisions between the reactant particles. There are a number of factors that affect the behavior of particles and have an overall effect on the rate of a reaction. So you can think about, we can look at this reaction here and we can look at it like we can look at it in this way. So imagine we can think about them like particles. So we have the hydrogen particles. So you have two, let's say, hydrogen atoms that are connected like this, and then you have another two that are connected here like so. And then what you have is you have these oxygen molecules. Okay, so you have two of these connected here like so, and then you have two of these here. And you have this chemical bond. So this chemical bond that's holding these atoms together, and there's also a chemical bond that's holding these atoms together as well. So literally, these guys here have to physically come into contact with this with the oxygen molecule. Okay, so this is your so these are your H2, and then these are your oxygen O2. So literally they have to physically collide with each other and come into contact. And not only do they have to collide, but they have to have enough energy to break these bonds. And then when the bonds break, essentially then what you're going to have, you're going to get this rearrangement of these atoms. So you'll get something that's like this. You'll get this new molecule. You'll get this new molecule being formed. And then you'll get a huge release of energy as well. Okay, so it's an explosive reaction. But the reactants have to physically hit off each other and come into contact with each other with enough force. So it's useful to think about the reactants like particles. And this is what's known as particle theory in chemistry. So what happens is the reactants physically come into contact with each other, and then what happens is you get this successful collision, and then you get a new product being formed. So old products in this case are being broken up, and new products then in this case are being formed. So then what are some of the factors then that impact on the rate of this reaction or the rate of reactions? So one is temperature, another one is concentration. So that's the amount of, for example, reactants that you have. The next is the particle size. Next is the nature of the reactants, and then we have catalysts as well. So we want to kind of look at these and get an idea of what we mean by it in relation to how it affects, like how quickly a chemical reaction happens. So if we have a look at this simulation here, so basically what we have is we have, for example, this chemical reaction that happens here. So this particle A comes into contact with this molecule here, AC, and then what happens is you get this new chemical being formed, AB plus C. So A is essentially joining on to C. Now, in order for A to be able to join on to this part here, it has to break the bond that's existing here. So in order for the reaction to happen, it has to hit. So if we start off, so what will happen is you can see here that it's basically coming into contact with the reactant, and then as a result of that, it is breaking the bond and it's attaching on, and a chemical reaction is happening. Now, what's happening then is that C is actually bouncing again and hitting AB, and then it's reversing the reaction. So this back and forth can happen. Okay, so you get this back and forth happening. So this is what's known as, this is like the basics of a chemical reaction. So basically the rate of the reaction is like how quickly products or reactants can be turned into products. So what are some of the things that we can do in order to increase the rate of the reaction? So we can do things like, so for example, we can add more reactants. So if I start adding in A, so we can see here that we're adding in some A's into the mix, and then I can add some of these guys. Okay, so what's happening is that they are physically bouncing and coming into contact with each other. But you'll notice that when there is a collision, there's no actual reaction happening. Why is that? Well, it's happening. There's no reaction happening because there's not enough force between the molecules. Okay, in order to break the old bonds and form the new. So one of the ways that we can increase the rate of the reaction is we can increase the temperature by heating up the solution. So when we heat up the solution, essentially what we're doing is we're adding energy to the reactant molecules. So what you'll see is that these reactant molecules will start to get more energy as the temperature goes up. And as a result of that, you can see then that they're colliding much more vigorously. Okay, and when they do collide, what's happening is then you're getting this new product being formed. So that's one way that the temperature, for example, impacts on the rate of the reaction. So the higher the temperature, the more energy these molecules will have, these reactants will have, and therefore the more collisions, and then the more successful collisions, the more the reaction happens. So again, temperature has a massive impact. The other thing that has an impact is the number of reactants or the concentration of reactants in the mix. So the more reactants you have, the more collisions you have, and the more collisions you have, the more the quicker the rate of the reaction. So that's one way in relation to temperature and concentration and how it impacts on the rate of the reaction. So we're going to look at these in a little bit of detail now. So what happens to the rate of the reaction when you stir a solution? So stirring the solution keeps the reactant particles in motion and increases the chances of collision and increases the rate of the reaction. So light sticks produce light because of a chemical reaction. Dropping a light stick into hot water makes it glow more intensely, demonstrating that the reaction occurs faster at higher temperatures. And it happens at higher temperatures because, like what we've seen, the reactants have more energy and they come into contact with each other. So when you raise the temperature, the particles have more energy, so they move around more quickly. This results in more collisions in a certain time, and so the reaction gets faster as we raise the temperature. So at 30 degrees, for example, and then at 40 degrees. So at 40 degrees, the reactants have way more energy, as we've seen when we increase the temperature, and there's a lot more collisions. So therefore, we are increasing the rate of the reaction. As particles get more energy, they move at greater speeds, and so there are more collisions and reactions get faster. So this is a chemical reaction here, okay, and we can demonstrate this in the lab. So when you raise the temperature of a system, the molecules bounce around at a lot more and are more likely to react. Okay, so this is basically an activity that demonstrates this. And what we find then is that after, like, when we complete the activity, we'll get like a table of results that looks something like this. So we can see that we've changed the temperature. So we started at 20, then we went to 40, then we went to 60. And what we can see then is that so after 1 minute, okay, the amount of gas that's being produced. So basically what happens is we have a solution here, and we have marble chip, it comes into contact with it, the gas comes out, and we get bubbles being produced. And what we can do is we can measure the amount of gas that's trapped inside here in the container. So after 10 minutes, for example, we get the volume of gas produced every minute. So we have 10 so at 20 degrees in a minute, we have 10 cubic centimeters. After 2 minutes, we have 20, 30, 40, and 50. Now we can see that if we increase the temperature by 20 degrees, it increases the rate of the reaction, or the amount of bubbles being produced, like what we can see here. And then again, if we increase the temperature even more, we can get that same increase in the rate of the reaction happening. And this is what it looks like on a graph. So basically, we can see that we have it graphed here using different colors. So at 20 degrees we can see this. So what we have is time along the bottom and the volume of gas being produced along the left hand side. So we can see that as we increase the temperature, the line gets steeper, and that results in more gas being produced and the rate of the reaction increasing. So generally, as we increase the temperature, the rate of the reaction increases as well. Another way that we can impact on the rate of reaction is the particle size. So what can happen sometimes is, like in that demonstration that we looked at, so we have a solid substance. So imagine this is our solid marble chip. So we have this solid substance, and then we have an acid. So we have this liquid, and this has to physically come into contact with the marble chip in order for the reaction to happen. Okay, so if we have, so the more like the acid can come into contact with the solid, okay, the solid marble chip, the more the reaction can happen. So what we can do in order to increase the rate of the reaction, we can reduce the particle size. So we can take our marble chip and we can break it up into smaller and smaller sizes. So essentially what that does is, so if we start off with a big lump like this, hydrogen ions can hit the outer layer of the acid. So the reactant particles can hit the outside of this piece of solid. Okay, so it can only react with the outer particles. But if we break it up like so, what happens is we get more surface area, or we get more areas where the reactant particles can physically come into contact with it. So remember, chemical reaction, the reactant particles have to physically come into contact. So what's the result of that? So if we have a solid that is reacting with a liquid, for example, if we reduce the particle size of the solid, we basically give more options for the reactant particles to collide with each other by like what we can see here. So therefore what that does is it will increase the rate of the reaction. So what happens to the rate of reaction when you increase the surface area? So surface area is a measure of how much surface of the reactant is exposed. When a large piece of solid material is cut into smaller pieces, its surface area is increased, and the smaller the particle size, the greater the surface area on which the reaction takes place, and the faster the reaction will happen. So an example of this is if we take potatoes, for example, and we want to cook a potato. That's a chemical reaction. If we want the potato to cook faster, we have to chop it up into smaller bits. Okay, so we take the potato and we chop it up. And as a result of that, you increase the surface area. So there's lots more, like basically the water can come into contact with much more parts of the potato when it's cut up like this. So what you're doing is you increase the surface area of the potato each time you cut it into smaller pieces. So as a result of that, the potato will cook faster. So reducing the particle size and increasing the surface area increases the rate of a reaction, or how quickly the reaction happens. So the effect of increasing the surface area on the rate of reaction, the steepest part of the curve is at the start, hence the fastest part of the reaction, but the curve becomes less steep as the reaction slows down and eventually becomes flat, indicating the end of the reaction. So this is just a timing of the reaction. So what we can see here is that so we have time, and then we have loss in mass in grams. So loss in mass in grams indicates, for example, the reduction of the reactant particles. And this is a way that we can look at a chemical reaction happening. So we can see that over time, the amount of reactants is reducing rapidly. And then what happens is, over a period of time, then it levels out, so we don't get any more loss. So you can see that this here is like the start of the reaction, and then this here is like the end of the reaction. So what we can say then is that like when we're talking about the rate of the reaction, we're talking about like a change in the concentration of either the reactants or the products. So concentration is like a count of the reactants or the products. Now in chemistry, we use this concept called the mole, and a mole is like a really, really big number. So it's 6.02 multiplied by 10 to the power of 23. Okay, so if you weigh out 12 grams of pure carbon, in those 12 grams of pure carbon, you have this number of carbon atoms. So it's a huge number. and this is like a unit that we use in chemistry to measure concentration called a mole. Now, a way to kind of think about it is it's just like the way we use, for example, a dozen eggs to count 12 eggs. Well, in chemistry, we use this concept called a mole, and that means that it represents, for example, the number of atoms or molecules of a particular substance that you have. But it's a huge, like it's a very big number. Okay, so just as an idea, if you measured out 12 grams of carbon, in that you would have 6.02 multiplied by 10 to the power of 23 atoms of carbon in that sample. This is an absolutely huge number. Okay, so that's a way to think about it. A dozen means 12 eggs. A mole of atoms means 6.02 multiplied by 10 to the power of 23 atoms. And we use it like, for example, an M, capital M to represent mole. So 1 mole means is equal to 6.02. So 6.02 multiplied by 10 to the power of 23 atoms. That's what a mole means. So what happens to a rate of reaction as you increase the concentration of the reactants? So when you increase the concentration, you increase the number of particles, which results in more collisions in a certain time, and so you get an increase in the rate of a reaction. That is, the reaction gets faster. So the more like reactant particles that you have, so if you increase the number of hydrogen atoms or the number of oxygen atoms, there's going to be more collisions. So therefore, because there's more of them, so therefore there's going to be more, there's going to be like a greater rate in the reaction. So the effect of increasing concentration on the rate of reaction, the reaction is fastest at the start. The steep curve becomes slower, the reaction proceeds. The curve on the graph goes flat when the reaction is complete as well. So we get this reaction mechanism that happens. So again, if we take this reaction here, so the marble chip with the hydrochloric acid, so if there's more molecules of the substance in the system, there is a greater chance that the molecules will collide and speed up the chemical reaction. So you have the marble chip and then you have the acid that's inside here. When they come into contact with each other, they react and they release this H2O and CO2 gas. Okay, so it's released as air bubbles and we can measure the amount that's released, for example, in here in this measuring cylinder. So what happens if we have a look at this? So when we increase, so if we start off with 1 mole, for example, of the acid, basically we get, so after a period of time, we can see the amount of carbon dioxide gas that's being produced as so, okay? And then if we increase the amount of acid and we increase it to 3 moles, so we increase its concentration, we can see that we increase the amount of CO2 gas being produced. So essentially what we're doing is we're increasing the rate of the reaction. And again, we can mark this on a diagram like so, or on a chart. So if we start off with 1 mole, this is what the rate of the reaction looks like. If we increase that to 3 moles, or we increase the concentration, we can see that we get much more, a bigger volume of gas being produced over a period of time. So what that says is that if we increase the concentration, for example, of the reactants, we increase the rate of the reaction because we give more opportunity for these collisions to happen. Now, the other thing that impacts on the rate of reaction is the nature of the reactant. So the type of atoms, for example, or particles that are coming into contact with each other at the start. So some atoms are very reactive, whereas other atoms are not very reactive. So the nature of some elements such as sodium and potassium are more reactive than others such as copper. And a list of metals in order of their activity is called the activity series. So if we have a look here, so here we have calcium. So calcium is very reactive, as you can see here. When it comes into contact with the product or the reactant, it reacts very, very vigorously. And this has got to do with the nature of calcium atoms. So this is the structure of a calcium atom, and we can see that it has this lone electron out here in the outer its outer orbital. And what happens is, as a result, this makes it very reactive. If we look at copper, for example, this is copper here, so it's not as reactive, okay, so it has a different structure, okay, or the nature of the reactant is different. If we take zinc, so again, zinc is fairly reactive as well because of its chemical makeup, the way that the electrons are arranged. And then magnesium then is the same as well, it's quite reactive. So again, the nature of the reactants, the substance that you use, some substances are very reactive, other substances are not as reactive. So it just depends on the nature of the reactant that you use. Another way that we can increase the rate of reaction or how quickly the reaction happens is using this thing called a catalyst. So a catalyst is a substance that can speed up or slow down a chemical reaction. So transition metals lie between group 2 and group 3 in the periodic table. Some well-known transition metals are iron, copper, chromium, nickel and gold. So transition metals, so these particular types of metals and their compounds are important catalysts. Okay, so they're used to speed up or slow down chemical reactions. So a catalyst is a substance which alters the rate of reaction without getting used up. And how will a catalyst affect the rate of reaction? So we have this thing called the activation energy, is the minimum amount of energy that a reactant particle must have in order for them to react. So when you add a catalyst, it lowers the activation energy, and this makes it easier for the particles to react. So there is an increase in the rate of the reaction. So a way to kind of think about this is if we take these particles here, okay, when they come into, they have to physically come into contact with each other. But like what we've seen in the demonstration, they have to have enough energy in order for the old bonds to be broken and then these new bonds to be formed. So we can look at that from an energy point of view. So what has to happen is these reactant particles have to have a sufficient amount of energy in order for them to be able to react. And that energy, or the amount of energy that they have to have so that when they collide they'll react, is called the activation energy. So if, for example, these molecules, these reactant particles have energy that's down here, really down here, what's going to happen is they will just bounce off each other. But if they have high energy, and if they have enough energy, they have let's say the energy gets up to here, so they have enough activation energy. So once the energy of the molecules gets up to this point, what will happen is the reaction will happen. So they won't just bounce off each other. So there's a fixed amount of energy or a certain threshold that has to be met in order for the reactant particles to have enough energy to break the old bonds and form the new bonds. And that's what's known as the activation energy. Okay, so what a catalyst does then is if you add in a catalyst, basically what it'll do is it'll lower the activation energy. So in order to get the reactants to react, you will need less energy than if you didn't use the catalyst. So it lowers the activation energy. So again, this is really important that you have an idea of these activation energies. So the red line here indicates when the reactants are mixed in together, but they don't have a catalyst, so it takes much more energy to get them to react. Whereas if you put in a catalyst, it reduces the amount of energy that's needed, so it increases the rate of the reaction. So this is how catalysts work. So they lower the activation energy of a reaction and allow it to happen. So in our bodies, we have these things called enzymes, and enzymes are biological catalysts. So they allow chemical reactions to happen. So enzymes, they control the rate of reaction with living cells. So we can do a demonstration of this. If we use liver and hydrogen peroxide, a reaction will happen and you'll get this foam that's being generated. And you can use this to measure the rate of the reaction, how much foam is produced. So liver contains an enzyme called catalase, which acts as a catalyst to break down hydrogen peroxide into water and oxygen. So basically how this works is you place 100 mils of hydrogen peroxide into a graduated cylinder, you add 1 cubic centimeter of liver to the hydrogen peroxide, and then you record the volume of foam that's produced after 20 seconds, and you repeat these steps until 1 cube of liver has been crushed in a mortar and pestle, and then you can record your results. So you can look at how a biological catalyst impacts the rate of a reaction. So the rate of reaction can be analysed by plotting a graph of the mass or volume of the product formed against time. And the graph below shows this for two reactions. Okay, so we can see that this reaction here is slow. We can see the curve here, and this reaction here is fast. Okay, so again, if we use a catalyst, we increase the rate of the reaction because we lower the activation energy. So the last thing then that we look at then are like other biochemical reactions. So we have that one with the catalase. Then we have this one here. So for example, if we think about photosynthesis. So photosynthesis is a chemical reaction. So again, on the left-hand side, you have the reactants. On the right-hand side, you have the products. And then in the middle, then you have the catalysts that get the reaction going. So there are several factors that can affect the rate of a biochemical reaction, such as respiration. So we have respiration and photosynthesis. So this here is photosynthesis. The main factors that affect the rate of photosynthesis are light intensity. So the more light you get, the more reaction that you get that happens. Carbon dioxide. So again, the more carbon dioxide or reactants you have, the more of the increase, it'll increase the rate of the reaction. And then the temperature then as well. So the temperature has to be just the right temperature in order for these reactant molecules to come into each other and for this reaction to happen. So these are biochemical reactions that can happen. Okay, so in this, we looked at, so students will be able to investigate the effects of a number of, so we looked at the different variables that impact on the rate of a chemical reaction, including the production of common gases and biochemical reactions, and as well like photosynthesis and the reaction of catalase. So that is the factors that affect the rates of chemical reactions.